So what we are going to start today, we are going to start the new chapter, I think chapter number 9 in your book. And we are going to discuss now a combination of inductor, capacitor, and resistive circuits. There are two different types of circuits we are going to discuss. One, when all three components are connected in parallel, that is parallel RLC. And then after that, of course, we're going to discuss if they are connected in series. These circuits are called second order circuits. Second order because you will see when we write the equation of these circuits, the equation is a second order differential equation. RL circuit and RC circuit that we discussed, they are called first order circuits because, of course, when you write the equations for voltages or equation for current, that's a first order differential equation. And in this case, you will see that we have a second order differential equation. And again, we have energy components, both inductor and capacitor. So they store energy and then they transfer energy. So the first circuits that we are going to be looking at will be the natural circuits. That is when the energy is stored in inductor and capacitor, and then you remove the source as we did with RL and RC circuit. Then how that energy is going to be dissipated from the inductor and the capacitor, and they will dissipate their energy, of course, through the resistor. And they also exchange the energy between inductor and capacitor as well. So all that discussion will be under parallel RLC circuits and under the natural response of parallel RLC circuits. So parallel RLC circuits, simply, we're going to start with the simplest one. That is, you have a source and you have a parallel RLC circuit, one resistor, one inductor, and one capacitor parallel to each other. And let's assume that the source can do current source. And let's assume this switch is going to open up at t is equal to 0, which is our reference time, R, L, and C. Voltage across all three components or all four components initially, when the switch is on, they will be the same because they are in parallel. And the voltage we assume as capacitor voltage. Three currents going into each component, one current into each component, three currents total. Now, when we are solving these type of circuits, when we are writing equation for these type of circuits, of course, we're going to drive the equation initially. And then when we are going to use those results that we're going to get from the equation, differential equation, we're just going to use those results to solve problems that we will be solving. You don't really have to do the derivation, of course, each and every time. You will just start with the results of the derivation based on the values of R, L, and C. And then we're going to go from there to solve for voltage or solve for current or power, whatever we're looking for. But initially, right now, we're going to do the derivation to figure out what will be the voltage across each component, that is the voltage across capacitor, inductor, and resistor. When we start solving the circuit, we use the same approach as we did for RL circuit or RC circuits. That is the first thing that we figure out is what are the initial values of the inductor current and the capacitor voltage. So the first thing that we figure out is IL0 negative. What is the initial value of the inductor current just before the switch opens up or just before the change happens in the circuit? And we see 0 negative. So these two values we have to figure out because we're going to use these two values when the circuit is running for a very long time after the switch opens up. we're going to use these two values to figure out different coefficients in the equation. Now, the reason we are finding these two values is what? Who can answer that question? Why we are specifically trying to find the inductor current before the switch opens up and the capacitor voltage before the switch opens up? Anyone can answer that question?
Would it be because you're trying to find um what it is, what the current is while it's charging?
No, that's not the reason. Anyone else can answer the question? All right, let me ask you the question for RL and RC circuit that we have discussed already. Why did we use to calculate the initial value of current IL0 negative in an RL circuit? Just RNL, or initial value of voltage in an RC circuit?
Find the voltage going across the element.
Gloriana, I can barely hear you. I think your mic, either the volume is low or the mic is not good. Chris, you want to answer the question?
Is it to calculate the step function?
Step function, no? In an RL circuit, you always find the inductor current, initial value of inductor current, IL0 negative. In RC circuit, you find VC0 negative. There was a specific reason we used to find those things.
Sorry, I didn't hear his response, but I was saying that it was to find the voltage going through the elements like the capacitor, the inductor.
No, that's not the answer to what I asked. Well, the reason we always find the inductor current just before the change happens and the capacitor voltage just before the change happens is because these values cannot change instantaneously. And the value of current passing through the inductor at 0 positive or just after the change happens, and the value of capacitor just after the change happens, they are the same as just before the change happens. So these values do not change instantaneously. And we use those two values just after the change happens. We use them as our initial conditions to get other values. In RL circuits, the initial condition that we used was the initial value of current just before the change happens, because that current value does not change just after the change happens. IL0 positive, IL0 negative is equal to IL0 positive. And similarly, in RC circuits, VC0 negative is equal to VC0 positive. And same goes for any circuit. As long as you have an inductor and a capacitor in a circuit, and you are making a change in the circuit, the current that is passing through inductor cannot change instantaneously. Hence, just after the change is going to happen, that current is going to be the same as what it was just before the change happened. And same goes for the inductor capacitor voltage. So that's why we find these two values, because these two values are the same as IL0 positive is equal to IS0 negative, and VC0 positive is equal to VC0 negative. So when the switch is going to open up and the source is going to become, is going to leave the circuit, it's not going to be part of the circuit. And then we will start solving for, the capacitor voltage, inductor current, whatever. Then we need to know what were the initial values of the inductor current and capacitor voltage to find our equations. And those values are the same as what the values were just before the change happened for the inductor current and the capacitor voltage. So those initial values do not change. And that's why we find those initial values at time t is equal to 0 negative. Okay, so the second question. What do you think if the switch is off or switch is on? Right now it is off. When the switch is on and the source is supplying current to the circuit and it's running for a very long time, what do you think is going to be IL0 negative? Who is going to tell me that?
I'm sorry, what were you looking for?
We are looking for IL0 negative, the value of inductor current just before the switch opens up, assuming that the circuit is running for a very long time.
Would it be, it would be the source minus the resistor current minus the capacitor current.
Okay. Anyone else? What will be the value of the inductor current just before the switch opens up, assuming that the circuit is running for a very long time?
Would it be the current that's going, also passing through the capacitor itself?
No. Anyone else? Now again, you have to think about how the components are going to be behaving if the circuit is running for a very long time, and then decide what will be the current, what will be the voltage.
Oh, would it be the same? It would be the same voltage if you were to take the same voltage that goes across the resistor, but then you take the derivative of it and multiply it by the inductor.
Okay, and that voltage is going to be what?
Well, it would be, oh my goodness. I want to say it's from the voltage from the current source, but I feel like that's wrong.
Okay, let me rephrase my question. How the inductor behaves, how the inductor and capacitor behave when they're running for a very long time?
The capacitor charges and the inductor discharges.
Anyone else?
Like an open circuit and a short circuit?
Okay, all right. Now, based on this answer, what you gave, now tell me what will be the initial value of inductor current.
It would be 0, wouldn't it?
Okay. Christopher, since you mentioned that capacitor will be open circuit and inductor short circuit, you tell me, what will be the initial value of the inductor current?
I'm not sure.
All right. So your capacitor, you said inductor will be short circuit, right, Chris?
Yes.
Okay. If inductor is short circuit, so it just closed, what will be the current passing through the inductor?
It will be part of IS.
Part of IS.
Oh, actually, if the capacitor is open, it will just be the current division between the resistor.
So
Actually, if it's shorted, all the current's going through it.
okay, that's the answer I was looking for. Why it is so hard, guys? If the inductor is short circuit, there is no current that's going to pass through resistor. Capacitor is open, so all the current IS is passing through the inductor if it is short circuit. At zero
Oh.
negative.
Now I see it.
At zero negative, all the current is passing through the inductor. Inductor is acting as a short circuit. Okay, next question. What will be the capacitor voltage initially at zero negative?
Would it be zero?
All right, explain why.
Because there's no current going through it initially? Because
There's
it's open right now, right? Oh, it's closed right now. Ooh.
all right. What will be the capacitor voltage? Anyone?
So if our capacitor would be a open circuit, our inductor is a short circuit. That means, would that mean that the voltage would be the same as across the resistor?
And that voltage will be?
The current source divided by the resistor.
Okay, is that the correct answer?
Current source times the resistor.
Is that the correct answer? Anyone? All right, you guys just told me inductor is short circuit. Capacitor is connected across the inductor. What will be the capacitor voltage?
Or wait, would it be zero? Because
Zero, it's connected across a short circuit.
yeah, because it's shorted, so it would be
Okay, so the initial values are Is and 0, and these will be the same values at 0 positive. Now you have to do this in every circuit. Not in every circuit it's going to be the same value. It depends upon how the circuit is arranged and all those things. But in general, and how long the circuit has been running before the switch or before the change happens. It could be different current value, different voltage values. But if these three components are connected in parallel, then of course, inductor is going to short out the capacitor and the resistor that is connected in parallel. Now, if there are other resistors connected in the circuit, of course, you will have to figure out the division of voltages, division of current. But if capacitor and inductor are connected in parallel, of course, capacitor voltage will become zero because inductor is going to short that out if the circuit is running for a very long time. So this is pretty easy. It's not difficult. Okay, so now we're gonna start evaluating when the circuit is going to become a natural circuit. That is, we're going to remove the source from the circuit. And to do that, we are going to write the KCL equation. We have current passing through resistor, inductor, and capacitor equals to 0 because the source current is out at t is equal to 0. Okay, now resistance current can be defined using Ohm's law. Vc over R. Vc is the voltage across all three components. Inductor current. How do you define inductor current in terms of its voltage? Anyone? What's the equation of inductor current in terms of voltage across inductor?
Is it 1/L VDT?
1 over L, go ahead.
VDT?
Integral.
Mm-hmm. The integral of VDT?
Plus the initial value of the inductor current. And the capacitor current. What is the capacitor current in terms of its voltage? Who's going to tell me?
If I
Yes.
remember correctly. Oh, you
Yes.
can go.
Yes, guys, go ahead. We did that so many times.
Oh, I'm sorry. I was just I'm in the open lab.
Is
so I was
it
getting
1
cut
over C?
1 over C.
Yeah,
1 over C what?
integral
No.
of
No.
Is it C dVdt?
C dV over
oh
C.
shit.
I know. I'm like, oh my gosh, is it the integral or the derivative?
You guys need to keep this, maybe create a formula sheet or something and keep it just in front of you. Instead of going through the notes, put all the important formula equations on a piece of paper and keep it in front of you for quick reference. Okay, now this is an integral differential equation, means you have integration and you have differentiation. Anytime you have multiple energy components, inductors, multiple capacitors, and so on and so forth, and if you write their current equation or voltage equation in the time domain, that equation is quite complicated. As you can see, you have only two components, and you have an integral differential equation. Now, this is rather easy to solve in time domain, but as the number of components increase, the equation becomes more complicated in the time domain. And instead of solving a circuit in the time domain, if you have multiple energy storage components, we move from time domain to Laplace domain, frequency domain, and then we solve the circuit, and then we come back to the time domain. But that's not the topic right now to discuss. We're just going to discuss how we are going to tackle this equation. So to solve this equation, first, we are going to take the derivative of both sides to get rid of the integral. So the other side is 0, of course, so that's still be 0. But we have to apply the same mathematical operation on each side of the equation to be consistent. So we're going to take the derivative of this. So 1 over R dVc over dt plus 1 over L, derivative and integral will cancel out each other, Vc, and derivative of a constant value will be 0, IL0 positive. And then C, this is going to become the second derivative. So this is why this is called a second order system, because the highest power of the derivative is 2. If the highest power of derivative is 3, it's called a third order system. We will rearrange this from highest power of derivative to the lowest power. And then we get rid of the coefficient with the highest power, so we divide the whole equation by C as well to get rid of this C. And we can write this down as Now, from RC circuits, we know that the natural response of capacitor voltage looks like what? Anyone can answer that question. What is the shape of the natural response of the capacitor voltage? Who's going to answer that question? We did that multiple times, of course.
Looks like an exponential curve.
Exponential function, very good. So the natural response of capacitor voltage is an exponential function. So the natural response is, we will write a general expression, A e to the power st. Now, of course, if it's a natural circuit, s is usually negative because your exponential function is going down. So this is the natural response of a capacitor voltage, whether that is in the first order circuit, second order, third order, whatever. This is how the capacitor is going to be discharged. If we take this expression and plug it in, let's call this equation 1. If we plug it in equation 1, let's see what we're going to get. By the way, this s that you see, that's a Laplace variable, although we are just taking it right now as a variable. But later on, you will see that this s is the Laplace variable. Okay, what will be the second order derivative of A e to the power st? Who can tell me that? A, of course, is a constant value, so we're going to take that A out. What will be the second order derivative of e to the power st? What is the first order derivative of e to the power st? E to the power x. What is the derivative of e to the power x or e to the power ax?
E to the x, it would just be e to the x. So would it be just a?
All right, guys. What is the derivative of e to the power st? E to the power ax, whatever you want to call it.
Would it be e to the power of st?
E to the power st, yeah. What will be that? A, of course, is constant. I took it out. What will be the derivative of e to the power st? The first order derivative, and then we can do this one more time to have the second order derivative. What is the first order derivative? Just to do the derivative one time. What will be the derivative of e to the power st?
Wouldn't it be s divided by e to the st?
No. Gloriana, you were saying something earlier.
I was saying, if it's a derivative, it should be e to the st.
Okay, and e
Um,
to the power st and
plus the constant.
yeah. Anyone else see? You guys should know what is the derivative of e to the power st with respect to t. The first order derivative. Don't worry about second order right now. What is the first order? You do the derivative one time. What will be the derivative of e to the power st?
Is it S e to the st?
S e to the power st. Yes, S e to the power st. That's the first order derivative. If you take the derivative again, what will be your result?
S squared e to the st?
S is square e to the power st. Thank you. One over RC. All right. A over RC rather. A is constant, and we just discussed derivative of e to the power st is S e to the power st. And then there's no derivative here, so e to the power st is equal to 0. So now what we are going to do, we are going to take a as a common factor, e to the power st as a common factor, and then in parentheses, we have s squared from the first term, 1 over RCS from the second term, and 1 over LC from the third term equals 0. Okay, so look at this equation now. A e to the power st times the quadratic equation that you see in the parentheses equals 0. What does that mean? That means that either your first term is 0 or your second term is 0. One of them is 0 means that the left-hand side is going to be equal to right-hand side. Either one of them is 0, the left-hand side will be equal to right-hand side. Now, can A e to the power st be 0? A e to the power st cannot be 0 because that's the response of the capacitor voltage. That's our solution. That's what we said. This is how the response of the capacitor voltage looks like. So this can't be 0. Which means that s squared plus 1 over RCS plus 1 over LC must be 0 in order for that equation to be 0. This equation is called, anybody remember what do you call this equation from math class, engineering math class or something? So I'm pretty sure you solved the second order differential equation in engineering math class. This is called characteristic equation. It is called characteristic equation. And as you can see, this is a second order equation, the quadratic equation. That means how many values are going to be there for S from this equation?
For the quadratic, 2.
2 values, right? So S will have 2 values, which will make this equation to be equal to 0, to be equal to the right-hand side. So if we solve this quadratic equation for 2 roots, S1 and 2, quadratic formula. Anybody remember what how to write quadratic formula?
Negative b plus or
Negative
minus
b, 1 over RC is b, plus minus.
square root of 4 minus AC.
No, first b square, 1
Right.
over RC is square, minus 4a, a is 1, and then c is 1 over LC. B square minus 4AC divided by
2a.
2. A is 1, of course. So I'm going to write this equation as negative 1 over 2 RC plus, I'm going to take this 2 in the numerator, and it's going to become part of the denominator, plus minus Oh, take this. When I take this 2 under the square root, it's going to become 4 because the square root of 4 is 2. So I can write this down as 1 over 2 RC square. And again, 2, if I take this 2 under the square root, it's going to become 4. So this 4 and this 4 will cancel each other. And I will be left with 1 over LC. And this is a very important equation. This is the result of that, your characteristic equation. Now, this equation can be written in terms of variable that we use very commonly as negative alpha plus minus alpha square minus omega naught square, where alpha is 1 over 2 RC, and this is called Napier frequency. Units are radian per second. And omega naught is 1 over square root of LC, because omega naught square is 1 over LC. And this is called resonant frequency. Units again are radian per second. So the two roots S1 and S2 are negative alpha plus square root of alpha square minus omega naught square, one root. And the other root is negative alpha minus square root of alpha square minus omega naught square. And our response, so S1 is negative alpha plus alpha square minus omega naught square, and S2 is negative alpha minus alpha square minus omega naught square. Now we had the solution that we said that the response, the capacitor voltage response goes down exponentially. Now we have two solutions. That means one solution is that Vc1t is A1 e to the power S1t. That's one solution. And Vc2t is A2 e to the power S2t, because we have two rods. And the general response of capacitor voltage, natural response, is A e to the power ST. That complete solution is going to be the sum of both. Complete solution for the natural response of the capacitor voltage is going to be Vct is equal to Vc1 plus Vc2, or A1 e to the power S1t plus A2 e to the power S2t. that will be the response of your capacitor voltage in the second order circuit if all three components are connected in parallel. Now S1 and S2, as you can see, negative alpha plus alpha square minus omega naught square and negative alpha minus alpha square minus omega naught square. Based on the values of Napier frequency, alpha, and resonant frequency, omega naught, you can have three situations. You can have three solutions. If alpha is greater than omega naught square, or if alpha is greater than omega naught, then the term under the square root is going to be a real term. It's going to be a positive value, alpha square minus omega naught square. And then you have two distinct roots, S1 and S2, two distinct roots. And both values will be negative. If alpha and omega naught are same, then the term under the square root is going to be 0. And then S1 and S2 are going to be the same, negative alpha for both of them. And if alpha is less than omega naught, then of course the term under the square root is going to be negative. That means you will have two complex conjugate roots. S1 and S2 will be complex conjugate of each other. Now, I hope everyone know what complex conjugate is. Anyone can explain what is a complex conjugate number? Let's say if you have A plus JB, what will be the conjugate of A plus JB? Anyone? You guys don't know what a conjugate of a complex number is? Yes, Chris, you're saying something?
Yes, is it numbers with the same real part but opposite imaginary parts?
Exactly. So A plus JB, the conjugate is A minus JB. Come on, guys. You guys need to know this, and this is basic math. A plus JB, the conjugate of the complex number will be A minus JB. And if you have A minus JB, the conjugate of that will be A plus JB. So if your omega is greater than alpha, if your resonant frequency is greater than Napier frequency, then your solution is going to have two complex conjugate root. So these three situations are called, or these three circuits are called overdamped circuit, underdamped circuit, and critically damped circuit. Damping types. The first damping type is overdamped circuit. If alpha is greater than omega naught, S1 and S2 will be two real and negative values. And the response of the circuit is the response of the capacitor voltage we can write. VCT is equal to A1 e to the power S1t plus A2 e to the power S2t. S1 and S2 are going to be negative values. So both are going to be exponentially decaying functions. For example, let's say alpha is 5 and omega naught is 3. Alpha is 5 means what? 1 over 2 RC is 5 and 1 over square root of LC is equal to 3. Alpha and omega naught, of course, both are functions of R, L, and C. So what I would advise you guys is to write a small program in MATLAB, your calculator, whatever you want to use. I don't care, MATLAB is easy. And in that program, you ask what are the values of R, L, and C. And based on those values, you calculate the values of alpha for the parallel circuit, and you do the same thing for series as well. When we discuss series, you calculate the value of alpha, you calculate the value of omega naught, and then you calculate the two roots, S1 and S2. Because you will be using those values in pretty much every problem that you're going to solve. So I don't see a point of taking time to calculate those values by punching in the numbers all the time. So just create a small code, whether you can create a function or just a small executable program. Ask for R, L, and C values, and the program should calculate alpha, omega naught, S1, and S2. Because again, you're going to be using these values to solve these RLC circuits, series or parallel both. Right now we are discussing parallel. Series circuits are the same, except the value of alpha is different in series circuit. The equation for alpha is different. Omega naught is the same, and of course S1 and S2 are going to be the same, negative alpha plus this and minus this. So write that code and keep it with you. I have written the code and I use it all the time, of course, because I'm not going to start punching in the numbers every time I'm solving this problem. I just give R and C, and then it gives me all those values that I use when I'm solving the circuit. So anyways, going back to this, if alpha is 5, omega naught is 3, then S1 is going to be negative alpha, negative 5, plus 25 minus 9. Alpha is square minus omega naught is square. Negative 5 plus 25 minus 9 is 16. Square root of 16 is 4. So that's going to be negative 1. And S2 will be equal to negative 5 minus, instead of plus, minus 25 minus 9. Negative 5 minus negative 4. So negative 9. So in that case, your capacitor voltage equation is given by A1 e to the power negative 1t plus A2 e to the power negative 9. A1 and A2 are the coefficients that we have to find out using the initial conditions that we calculated. We're going to do that when we solve circuits. But just to show you that for overdamped circuit, this is how the shape of the equation is going to be. You will have two exponential, which are going to be going down because these are negative values. So these are exponential, the decaying exponential functions. And then, of course, from the circuit, you will find what is the value of A1 and A2 based on the initial conditions that we're going to discuss when we solve circuits. So this is the shape of overdamped circuit response. If you plot this response, you're going to have an exponentially decaying function from the first term and an exponentially decaying function from the second term. Both are going down. And the sum of those two functions, of course, is going to be exponentially decaying function, which again is going down because it's a decaying function, of course. Now we use the term significant root. Significant root or significant frequency. What's a significant root or significant frequency? And that term you're going to use here, circuit analysis. Anytime you have, exponentially decaying function versus control systems, circuit analysis, power electronics, signal processing, anywhere, you will see this term, significant root or significant frequency. Significant root or significant frequency basically is the root or the frequency that is going to take longer to decay, because your shape of the curve depends upon which term. If you have 5 exponentially decaying terms, let's say, right now we have 2, well, let's say you have 2, 3, 4, and all of them are exponentially decaying. The term that is going to take the longest time to decay, that term is going to define shape of the curve. And the frequency corresponding to that term, or the root corresponding to that term, is called the significant root or the significant frequency. We can write this in terms of time constant as well. Remember, we discussed time constant last time, or in the last chapter. In terms of time constant, we can write this down as a1 e to the power negative t over 1 plus a2 e to the power negative t over 1 divided by 9. So a e to the power negative t over tau, that was what we discussed as the natural response of RC circuit and RL circuits. So if you want to write that down, write these terms down in terms of t over tau, then of course we can convert those S1 and S2, put them in the denominator, and then take the reciprocal of those. So now this can be our tau 1, and this can be our tau 2. It's the same equation that is written on top. So the significant root is going to be the one that is going to take longer to decay. Now, who is going to tell me out of these two terms, which term is going to take longer to decay?
That would be the second root.
Second term, this term.
Yes.
It's going to take longer to decay. Okay, anyone else? Is the second term or the first term?
My gut reaction is the second term.
Okay. All right. So everyone is saying second term. How long? So for the second term, the time constant is 1 over 9. For the first term, the time constant is 1. How long the first term is going to take to go to 36% of the initial value, A1? Come on, that's not a trick question.
It's the value of tau.
Value tau. And what is the value of tau? 1. It's going to take 1 second to get to 36% of the initial value, which is A1. How long the second term is going to take to get to the initial value A2?
1/9 of a second.
1/9 of a second. 36% is 1/9 of a second, which is faster, 1/9 of a second or 1 second?
1/9 of a second. So it should be the
1/9 of the
first.
second is faster. That means the term that is taking longer to decay, is the first term. It's taking 1 second to go down to 36% of its initial value. The second term is taking less amount of time to go down to 36% of its initial value. So the significant root is not the second one as some of you told me, because that's dying down quickly. It's taking 1/9 of a second to get to 36%. It's dying down quickly, 2/9 of a second to die down even further. The first term is taking 1 second, 1 whole second to die down to 36%. And then of course, it will keep on going. So the significant root is the one, or the significant frequency is the one that takes longer to die down, because that term is going to define shape of the curve. The one that dies down quickly, that's not going to contribute much to make the shape of the curve. But the one that is going to last longer, that is going to contribute to make the shape of the curve. So it's the first term in this case. So the significant frequency is the frequency which is the smaller value of S1 is the significant frequency, or correspond to the significant frequency. That is, that term is going to take longer to die down. That term is going to define the shape of the curve. In terms of time constant, of course, as you can see, again, the higher the number, the smaller the time constant. The higher the frequency, the smaller the time constant. The smaller the time constant means it is going to die down quickly. It's going to take less amount of time to get to 36%, and then other values. So keep that in mind, because that you will see in many classes, because when you're plotting the curve, let's say if I'm plotting the curve of this, if I know the values of A1 and A2, and I'm plotting the curve. When you're plotting the curve, you plot corresponding to the term that is going to take longer to die down, because you don't want to plot it for a shorter amount of time, and the term that is dying down is still not gone to 0. So you use the time for the corresponding to the significant root or significant frequency. So if I'm plotting this curve, let's say, and I see that my significant frequency is 1, or significant, the root or time constant is 1 second, then I will plot this for approximately 5 to 6 tau. Like in the lab that you did, you use 6 tau to see that, okay, it has died down properly in 6 time constant. So I'm going to plot this curve for 6 seconds at least, in order to make sure that my term that is dying down, that is taking its time to die down, would have been died down properly within 6 seconds. The first term is faster, so that's going to die down quickly anyways. So if you're plotting this curve, plotting the response, then use the significant root and then estimate how long you are going to plot the curve. So that's important thing that you need to know and you need to understand, not only for this, because this you're going to see, as I said, in control systems, in signal processing, in power system, in pretty much every class you will see the second order system, and you will have to plot them and do all those things. So significant root, significant frequency, they are important aspects of these systems. So the response is going to look like 2 exponential terms, both dying down, one dying down faster than the other. The term that is dying down faster, that's not significant. The one that is taking longer, that's significant. All right, the second type of systems are called underdamped systems. So these are the overdamped system in which both roots are real. And the second type of systems are called underdamped systems. In underdamped systems, alpha is less than omega naught, which implies this term is going to be negative under the square root. So I'm going to write this down as negative alpha plus j omega naught square minus alpha square. Because of course, anytime you have a negative under the square root, that's going to be a j complex number. I'm going to put j, and then I'm going to switch the order of that. Omega naught square minus omega naught square minus alpha square. And this is what we represent as omega d, or sometime in some of the books, as you will see, it is represented as omega n as well. And omega d or omega n, they are called natural resonant frequency. Natural resonant frequency. So now your two roots are S1 is negative alpha plus j omega d. Omega d is omega naught square minus alpha square. And the second root is going to be negative alpha minus j omega d. So these are complex conjugate of each other. How the response is going to look like? Capacitor voltage response. VCT A1 e to the power S1t plus A2 e to the power S2t. So if I put A1 e to the power S1, if I put negative alpha plus j omega d t, and for A2 e to the power negative alpha minus j omega d t. I can simplify this. A to the power negative alpha t e to the power j omega d t, A2 e to the power negative alpha t e to the power negative j omega d. And then my the common factor is e to the power negative alpha t, and then I can write this down as A1 e to the power j omega dt plus A2 e to the power negative j omega dt. Okay, anybody here remember Euler's identity? E to the power jx. Anybody remember this? What is, if you expand e to the power jx in terms of trigonometric function, what do you get?
You're referencing cosine and sine, correct?
Yep. Tell me, Lazaro.
So that would be, if I remember correctly, it's A1 cosine.
No, just e to the power jx. What is e to the power jx when you expand that?
Oh, that is cosine x plus j sine.
Very good. Cosine x plus j sine x. And likewise, e to the power negative jx is cosine x minus j sine x. So this is the Euler's identity. So if we apply Euler's identity to our exponential function here in this term, we can write this down. Write it down here. E to the power negative alpha t a1 cosine omega dt plus j sine omega dt plus a2 cosine omega dt minus j sine omega dt. So I'm gonna take the common terms now, cosine omega dt. So e minus alpha t cosine omega dt a1 plus a2 plus J. Should put A1 plus A2 first, actually. Not good. A1 plus A2 cosine omega dt plus J A1 minus A2 sine omega dt. Now, when you calculate the values of A1 and A2 from the initial conditions and whatever, and if your circuit is underdamped, A1 and A2 are going to be also the complex conjugate of each other. A1 and A2 will also be complex conjugate of each other. So if A1 and A2 are complex conjugate of each other, I'm going to continue. Of course, I cannot continue here, so I'm going to continue right here. Let me write down continued. If A and A2 are complex conjugate of each other, let's say A1 is A plus JB and A2 is A minus JB. Then A1 plus A2 will simply be 2A, and A1 minus A2 will simply be what? J2B. So when you put A1 plus A2 to A here, that's going to be a real number. And when you put A1 minus A2, J2B, J and J is going to multiply together, and that's going to become -1, let's say. So again, A1, J A1 minus A2 is also going to give you a real number. So both A1 plus A2 and J A1 minus A2 will become real number, because when for the underdamped circuit, when you calculate A1 and A2, they are complex conjugate of each other. So the response of the underdamped circuit is given by e to the power negative alpha t. A1 plus A2, we just call it B1. And J A1 minus A2, we just call it B2, whatever the value is going to be for B1 and B2. And that is the response, natural response of underdamped circuits, capacitor voltage. This response has two terms, of course. It has an exponential term, which is the Napier frequency, and it has the trigonometric terms. And those terms have natural resonant frequency. So if you plot this response is a combination of what we call, or this response is called exponentially decaying sinusoidal function. So it's going to be something like this. So it's going to be a sinusoidal function, but because of the exponential decay, e to the power negative alpha t, that sinusoidal function is decaying. And eventually it's going to become zero, because exponential term is going to become zero when time hits infinity, mathematically. Of course, after a few time constants, 6 time constant or so, it's going to go down to zero practically, pretty much. So this is the exponential decay that corresponds to the Napier frequency. And this sinusoidal frequency corresponds to natural resonant frequency. So the frequency of this sinusoid is omega d, radian per second, and you can calculate from radian per second what is the frequency in hertz. Of course, radian per second is omega is 2 pi f, as we know. So you can calculate what is the frequency of hertz of this sinusoid. And how fast or how slow it is going down, that depends on the Napier frequency, alpha value. Remember, time constant. So if alpha is smaller, it's going to take longer to decay. If alpha is larger, time constant is going to be smaller. It's going to take very short amount of time to decay. So you may have like one cycle of sinusoid if it is going down fast. But if it is taking its time to go down, so for example, if the natural resonant frequency is much larger than alpha, then if it is much larger than alpha, alpha is going to, or the time constant corresponding to alpha is going to take its time to decay. But since omega d is much larger, it is going to oscillate many times before it goes down to zero. So you will see many oscillations. And the second order system, the natural resonant frequency or the underdamped response, again, it's extremely important, not only in circuit analysis, but in control systems and signal processing, power systems, everywhere we use this response. So once again, understanding is important. So understand how the response is going to look like, what factors are going to affect this response. Two factors that are affecting this response is alpha and omega t. Alpha is the Napier frequency that defines the envelope, how it is going down, exponential function, and omega d defines how many times it's going to oscillate. What is the frequency of oscillation of this waveform? But this is the this is basically the shape of the response that is for the underdamped circuits. And before we take a break, I'm just going to do the third one quickly, which is the critically damped circuit, which is the third one. So critically damped circuit is when alpha is equal to omega naught, which means S1 is equal to negative alpha plus alpha square minus omega naught square. This is going to become 0 if both are equal, and S2 will be the same. So both S1 and S2 are going to be the same. So in this case, your response actually is not just the combination of both, like A1 plus A2 e to the power negative alpha t. Your response is, in this case, e to the power negative alpha t, A1 plus A2t. So it becomes a linearly exponential decaying curve. E to the power negative alpha t, which is the Napier frequency, A1 plus A2t, which is a linear function. So it's going to be a linearly decaying exponential curve. So these are the three types of systems that you are going to see for the second order RLC circuit, whether they are parallel connected in parallel or connected in series. So once you understand this, when we do the series connection, it's going to be exactly the same thing. The only thing that will be different is alpha. Alpha, instead of 1 over 2 RC, it is going to be R over 2L. So that equation is going to be different. Rest of the things, rest of the understanding of significant root, second order, the underdamped system, and all those, they will exactly be the same. So if you understand this correctly, the series RLC circuit are going to be just a breeze. It shouldn't take that long. So based on the damping type, we'll have different different response types, the response equations, VCT. Overdamped circuit is this: A e to the power S1t, A1 e to the power S1t plus A2 e to the power S2t. Underdamped circuit is E negative alpha t, B1 cosine omega dt plus B2 sine omega dt. And critically damped circuit is e to the power negative alpha t, A1 plus A2t. Our goal is to find first the value of alpha, the value of omega naught, S1 and S2. 4 things. And as I said, those 4 things, you can just create a small program, because those equations you can just put in the program. Every time you run the program, you ask for R, L, and C, and the program should give you the values of alpha, omega naught, S1, and S2. It will tell you, of course, based upon the values of R, L, and C, it will tell you if it's a if it's an overdamped circuit, that is if S1 and S2 are real. If it's an underdamped circuit, that is S1 and S2 are complex conjugate of each other. And if it's critically damped circuit, then S1 and S2 will be exactly the same. And those values will help you writing this equation down. And then your goal is going to be to find the 2 coefficients, A1, A2, B1, B2, whatever you're looking for. And those 2 coefficients we will find using the initial conditions that we will find before the change is going to happen. So that's the process of solving these circuits, which is a simple process. The toughest part is going to be to find A1, A2 or B1, B2, because that you will have to apply some circuit analysis to find those values. Easier part is to find what type of damping is that, because again, you can just put it in the program and it's going to tell you what are the roots. Based on the roots, you will know what is the damping type, or based on the value of alpha and omega naught, what is the damping type. So we will continue our discussion after the break. We'll take a 10-minute break, and then we're going to start solving some problems to see how we're going to find A1, A2, and all those things. So I'm going to pause. Yeah, give me a second. I'm going to pause the recording, and then I'll discuss whatever you want to discuss. Problem number 1. Okay, let me take help from my older problem. Let's see, R is 6, L is 7, and C is 1/42. Okay. So let's say we have a current source. IS is, let me see what the value is. IS is 10 ampere. 10 U negative T. R, L, and C. C is 1/42 farad. And R is 6 and L is 7. 6 ohms and 7 Henry. And we are going to calculate the capacitor voltage. Determine and plot. We're going to calculate that and plot that as well. VCT for t greater or equal to 0. Okay. Let me share my whole screen so I can show the MATLAB work as well. Share a screen, everything.
Professor.
Yeah.
Does that say 1/42 farads?
1/42 farad, yes.
Okay.
So as I said, the first thing we're going to do is we're going to find out what type of damping do we have in this circuit. So we're going to find out alpha, omega naught, S1, and S2. 1 over 2 RC, 1 over a square root of LC. Okay, so I'm going to use the program that I have written. This is my parallel RLC transient circuits. I'm going to ask user to enter RL and C, and then calculate alpha, omega naught, omega d, all those things that you can see that we will do that. So simple equations I just put in there. RL and C. R is 6, L is 7, and 1 over 42 is C. And that gave me alpha 3.5 radian per second, omega naught 2.5 radian per second. And since alpha is greater than omega naught, which means that our two frequencies are real, S1 and S2, as you can see, and this is an overdamped circuit. I also calculated, of course, omega d. Omega d doesn't really matter in this case because, of course, there's no natural resonant frequency in this case, but I just calculated in case if it's a underdamped circuit, so omega d value is going to be important. And FD, of course, correspond to omega d, the frequency in hertz, and TD is the time period corresponding to FD. So all those things are they come in handy. But omega d, FD, TD, they're all valuable values if your circuit is underdamped. But if your circuit is overdamped or critically damped, we don't really use any of these values. All you need is alpha, omega naught, S1, and S2. So in this case, alpha is 3.5, omega naught is 2.5. 3.5 radian per second, 2.5 radian per second. And then we have S1 -1 and then -6. -1 and -6, both radian per second. These are all angular frequencies, radian per second, not the cyclic frequency. Cyclic frequencies are in hertz, how many cycles per second, and angular frequencies are in how many radians it is going to move in 1 second, radian per second. So our overdamped circuit, overdamped response. So the capacitor voltage expression is going to be A1 e to the power S1t plus A2 e to the power S2t. A1 e to the power -1t plus A2 e to the power -6t. Of course, volt for t greater or equal to 0. A1 and A2 are the two coefficients that we are going to find using the initial conditions. We have not defined the initial conditions yet, so we're gonna first find the initial conditions. That should be the step number 1, but I did this, but that's fine. Okay, before we find the initial conditions, and then using those initial conditions, we find what are the values of A1 and A2. Who's going to tell me which root is the significant root? That is, when we are plotting this response, what time constant should we take in order to plot this response?
-6.
You're going to take -6. So what will be the time constant corresponding to -6?
Never mind. That'd be 1/6. So take the 1.
Yes, so answer is you're going to take 1 because 1/6 is smaller than 1. So the time constant or the root, which is 1 radian per second, and S2 is 6 radian per second, 1 is going to take longer as compared to the root 6 because the time constant corresponding to 6 will be 1/6, which is smaller than 1/1 or 1. So when we are plotting this curve, we are going to take the time constant of 1, and then we're gonna just plot for 6 time constants like we did for the lab that you did last week or Monday, not last week. So we're gonna plot for 6 seconds, and then we're going to divide that into like 100 points or 200 points to have the smooth plot. So again, the concept of significant root is important, remember, especially if you're doing the plotting and trying to figure out the values from the plot. Now, to get the values of A1 and A2, we are going to analyze what are the values of, we're going to find the initial conditions. So initial conditions. IL0 negative and VC0 negative. All right, now from the circuit, who is going to tell me from this circuit what will be IL0 negative and what will be VC0 negative? What will be IL0 negative? By the way, how the source is behaving in this circuit?
It's acting when it's negative.
It is active when it is negative, and when the time is positive. What's going to happen?
When the time is positive, it's not acting.
Okay, so what's going to happen to the source physically? How are you gonna, well, not physically, but how are you
You're
gonna
gonna move the source.
say it
Or
again?
you open the source.
It's going to open it because the current source, very good. So when time becomes 0 or greater than 0, the source is going to open up. Before that, it has the value of 10 ampere. So what is the value of the inductor current before at t is equal to 0 negative?
10 amps.
Say it again.
10 amps.
10 amps. Okay. And what is the value of the capacitor voltage?
Uh, 0
0. Why?
because it's open.
Didn't we just discuss it like when we were discussing this circuit? 0 is the correct answer, but it's open is not the correct answer.
It's because the inductor is shorted.
Yes, because the inductor is shorted, and that's why the voltage across the capacitor is going to be 0. We discussed that a few minutes ago. So the initial value of inductor current is 10 ampere, and initial value of capacitor voltage is 0 volt. 10 ampere and 0 volt. So these are the two initial values that we are going to use, and they will not change right after the change is going to happen. That's why we are using those values. Okay. So now, to find the values of A1 and A2, again, this is a standard procedure, remember. So this is going to be pretty much the same. The only difference is going to be how the circuit is given and how you're going to analyze, the two equations that we will have to develop, as you will see. So the first thing we're going to do is we are going to evaluate this equation of VCT at t is equal to 0 positive. At t is equal to 0 positive, just after the change happens. 0 positive means 0, basically. VC 0 positive equals A1, and e to the power 0 will be 1. So both e to the power s1t and e to the power s2t, both are going to become 1 when you put t is equal to 0 or 0 positive. So you're going to have an equation A1 plus A2. And VC 0 positive is 0. So you will get equation number 1, which is A1 plus A2 is equal to 0. That's easy. The first equation is always easy. For the second equation, because you have to find two coefficients, A1 and A2. You cannot find them from one equation. You have to have at least two equations, linear equations, and solve them simultaneously to find the values of A1 and A2. To find the values, to find the second equation with A1 and A2, what we do is we take the derivative of the capacitor voltage equation. So also, and then we evaluate that equation, the derivative equation at 0 positive. So first we take the derivative. All right, when we take the derivative of the capacitor voltage equation, which is right here, what will be our derivative from this equation right here? Or right here, whatever we can just go with general equation, because that equation is not going to change. What will be the derivative of a1 e to the power s1t plus a2 e to the power s2t?
It would be A1 S e to the power S1t plus A2 S2 e to the power S2t.
Very good. S2 e to the power s2. Okay, very good. And now we are going to evaluate this equation, the derivative equation, at 0 positive. So e to the power 0 again will become 1. So we will have a1 s1 plus a2 s2. Okay. dVc over dt. I is equal to C dVc over dt. So dVc over dt is basically IC over C. We know that IC is equal to C dVc over dt. So dVc over dt is IC over C. dVc over dt is IC over C, and we are evaluating the current at 0 positive. So at 0 positive, what is the value of the capacitor current? A1 S1 plus A2 S2. Now from the circuit, how we can write the value, how we can write down the expression for the capacitor current from this circuit? Who's going to tell? In terms of the other two currents. Like KCL. Using KCL, what will be IC?
IC will be
Sorry.
Go ahead, one of you, whoever want to go. Yes. In terms of KCL, what will be IC?
It would be IS minus IR.
IS is not there. We are evaluating for t at t greater than 0.
I'm sorry.
We are evaluating when time is greater than 0. So IS is not there.
Oh, so that means that the capacitor would be like the source, correct?
I'm just simply asking, in terms of KCL, what will be the equation for IC?
Oh, would be IR plus IL plus IC equals 0.
That's KCL. So what will be IC? What will be IC equals what?
IR plus IL.
No.
No.
You just said IC plus IL plus IR is equal to 0. So from that equation, what will be IC?
IC would equal
IC equals IR minus IL.
no, it would be IC would equal IR plus IL.
You guys, you just told me this, right? And I'm asking you, what is IC from this equation?
IC equals negative IL
Negative
minus
IR,
IR.
negative IL minus IL. Yeah, exactly. So IC 0 positive is negative IL 0 positive minus IR 0 positive. Okay, we know what is IL0 positive. We found that value using initial condition, which is 10 ampere. The question is, how are you going to find out the resistor current at t is equal to 0 positive? What will be, how are you going to find IR from the circuit? Who's going to tell me that? What is the expression for IR from the circuit? Natural circuit, of course, IS is gone at that time. What will be the expression for IR? Come on, look at the circuit.
So could we just use that IC plus IR plus IL?
We already used that. My question is now, what will be IR equation from this circuit? Natural circuit, of course, IS is gone.
Would
You
it
have,
be
you have different variables on the circuit. In terms of those variables, how are you going to write down IR?
wouldn't IR be equal to negative IC minus IL?
No, we already used that equation to write down IC. What is the voltage across R? In terms of variable that you see on the circuit, what is the voltage across R?
It would come, well, we don't have the current source. So it would be the discharge from the capacitor.
In terms of the variables that you see on the circuit, anyone, what is the voltage across R?
The voltage across IR
You do
is
voltage across R, not IR. R.
IR times 6.
What is this?
So voltage across the capacitor.
Yes, and that voltage is also
The
across
voltage
the
across
inductor,
IR.
across the resistor. The voltage across R, L, and C is VC. You can see that on the circuit. It's not hidden. It's there. That's what I said. What is the voltage across R in terms of the variables that you see on the circuit? Okay. If you know the voltage across R, how are you gonna write down the expression for IR?
Oh, sorry, I think I was muted. Isn't it voltage VC over R?
VC over R, yeah, Ohm's law. I mean, come on. VC over R. So IR0 positive can be written as VC0 positive over R. And what is the value of VC0 positive? 0. That means initial value of resistor current is 0, which makes sense because remember, the current that is passing through inductor is not going to change within an instant of time. So all the current that was coming before t is equal to 0, it is still going to be going through inductor right after t is equal to 0. So this current is going to be 0, capacitor will still be acting as an open circuit. because capacitor voltage cannot change instantaneously, and the voltage across capacitor will still be 0. So all the current that is passing through RL and C, all of that current will still be going through the inductor, because again, inductor current cannot change instantaneously, and capacitor voltage cannot change instantaneously. So this voltage is 0, this current is 10 ampere. So our equation is going to be negative 10 ampere over C, this is 0, equals A1 S1 plus A2 S2. And that is our equation number 2. So now we have two equations. Equation number 1, A1 plus A2 is equal to 0. Equation number 2, A1 S1 plus A2 S2 equals negative 10 over C. And solving these two equations simultaneously will give us the values of A1 and A2. So my first equation, let's say I keep A is equal to, my first equation is A1 coefficient is 1, A2 coefficient is 1. And in my second equation, A1 coefficient is S1 and A2 coefficient is S2. So S1 and S2. And my constant vector on the right-hand side, from the first equation is 0. And from the second equation is negative 10 over C. I don't think I used the value of C. Yeah, I did actually. 1 over 42, I think. So negative 10 over C. In my program, it already assigned C as 1 over 40. So the values of A1 and A2 are going to be, let me just call them whatever Q is A / K. So A1 is negative 84 and A2 is positive 84. Solving 1 and 2 simultaneously. A1 is negative 84 and A2 is positive 84. A1 is negative 84 and A2 is positive 84. Which implies our equation is for capacitor voltage A1 e to the power S1t and A2 e to the power S2t. So I'm going to put down positive value first. So 84 e to the power negative, what was the S1 and S2 values? Negative 6 and negative 1. Negative 60 minus 84 e to the power negative t, or 84 is common, e to the power negative 6t minus e to the power negative t. Volt t greater or equal to 0. So this is our capacitor voltage equation.
Dr. Ijaz, can you scroll up just a little bit? Thank you.
Well, guys, any question about this problem? Standard steps, remember, but again, when you're finding, specifically when you're finding the derivative and then you're plugging in the current and then later on you're going to plug in the voltages, then you have to look at the circuit and decide how you're going to write that equation of IC0 positive in this case, or VC0 positive, IL0 positive, whatever you're putting down. That's coming from the circuit. So pretty much the only hard part in these problems is the last part. When you take the derivative of, in this case, the derivative of the voltage equation, and then you plug in the equation for IC0 positive. That's the only tricky part in this equation. Rest is pretty much the standard process. Okay, so if we are plotting this, since we also have to plot it, the first thing that we do plot, as we discussed in MATLAB, first you do is you define, of course, you're plotting against time, so you're going to define a time value, a time vector. So, of course, the root 1 is correspond to the larger time constant S1. So we're going to take that, which is 1. So let's take that as our time constant, which is 1 second, and divide. We're going to plot for 6 time constants. So divide the whole interval in 100 points maybe. So let's say 6 divided by 100 up to 6. So we're plotting for 6 time constants. 1 time constant is 6, the significant root, that is. And I'm dividing the whole range in 101 point in this case, because we're starting at 0. And then we're going to write our equation down. VC is equal to 84 times exponent of negative t plus, or minus rather, exponent of negative 6t rather, 6t minus exponent of negative t. And then we'll just do the plotting. Plotting t versus VC. And I'm going to use a little thicker line. So I'm going to call line width 2 to make the line thicker. X label is time. And Y label is VC of t. So this will be the plot that you're going to get. See if I can squeeze it on the previous page. Yes. Oh, we did not do VCT. Yes. Can perform indexing operation. Function type. Okay. Oh, should be a comma here. Yeah, but I did not print VCT because I put a period over there. Anyway, so this is VCT on the y-axis. This is time, and this is VC versus time. So this is the plot. So first define the time vector, write down the equation. Time vector is defined based on the significant root, and I'm plotting for 6 time constant. 6 times the significant root, and then just plot. I divided total number of points into 101 rather, so that my plot is smooth. Because if you plot few points, the plot is not going to be smooth. 100 points should be good enough for this range. So as you can see, the voltage started at 0 as we expected. Then the voltage start going down, that is, it start charging in the opposite direction. Why it started charging in the opposite direction? Because inductor current was flowing. Inductor current didn't go down to 0. Inductor current was flowing, and inductor current is going to start supplying voltage, start supplying current to both capacitor and resistor. So the capacitor is going to start charging in the opposite direction. Plus minus, as you saw here, is going to start charging at the bottom. So it's going to change its polarity, plus and minus. Finally, the capacitor is going to be charged fully. As you can see from the curve, capacitor is going to be charged fully at this point, at this instant of time, whatever that instant of time is. And then the capacitor will start discharging and start giving up its charge through the inductor and then through the resistor. And eventually capacitor voltage is going to go down to 0 again when it is fully discharged. So that's what this curve shows us.